Welcome to the Introduction and Operation Guide for measuring MIPI DSI signals using the Bus Finder Protocol Analyzer. Let's start by launching the software and selecting the Protocol Analyzer mode. Click on the protocol list in the upper left corner. We'll choose MIPI DSI. If you purchase the D-PHY option, both DSI and CSI protocols are included. For display interfaces, we also offer an EDP protocol option. For memory interfaces, available options include DMMC, SD 3.0, SD 4.0, UFS, and NAND flash. Let's return to MIPI DSI. We'll cover the settings section in just a moment. In this demo, we use a Samsung S8 Plus and change its screen resolution. Since it uses DSC, it sends a 0A command to switch the PPS, allowing us to decode and restore the image. The bus finder streams captured data directly to the PC hard drive in real time, and its 32 GB memory is used as a buffer. Once it fills up, capturing stops. This phone uses command mode architecture, which generates less image data, allowing for long-term capture. Here is the protocol decode report window. On the left is the timeline. The next column shows mode status like low power, bus turnaround, ULPS, and high speed. VC stands for virtual channel and ranges from 0 to 3. The data type and DCS commands are decoded automatically. WC, or word count, shows how many bytes follow the command. The data column shows the first few bytes of the packet. You can also see the direction of data, as well as ECC and CRC results. On the far right, you'll find information like packet speed. About 900 megabits per second here, with a clock around 450 MHz. Click on any packet to view detailed decode results and raw data on the right. The navigator function categorizes all packets. Click Report List, then go to Statistics list to browse by category. For example, you can find all long write packets. Double-click any entry to jump to its location in the main report. You can also find categories for DCS commands, packet count, image frames, and error types such as single-bit or multi-bit ECC errors. You can export the data as a text or CSV file. The Hide Items function lets you temporarily hide unneeded data. For example, if you only want to see command packets and not video data, you can check EOTP, Null Packet, 2C, and 3C, then click Apply. The system will now only display command-related packets. This feature is especially useful when dealing with large volumes of protocol data. Clicking Clear will restore all hidden packets. You can also restore the image. First, select the virtual channel, in this case, VC0 only. Then choose the format type. Here, it's DSC command mode. There are two ways to set up the PPS. You can import a PPS file in text format or let the system automatically extract the PPS when a 0A command is detected. If the device does not send 0A commands, manual input is required. Click Process to begin image restoration. The result can be saved as an image file or raw binary data. The Save button is in the upper right corner. The restored image result also links back to the corresponding 2C packet in the main report. Here we use data captured from another device, an iPhone X, for demonstration. If DSI transmits image data in video mode, the Porch function can analyze the format of each frame. The software decodes full image layout parameters like VSA, VBP, VACT, and VFP, and displays line counts and timing for each frame. Let's go over the settings. On the left is the hardware connection setup. You can change lane assignments or swap P and N in the software. You can also select the number of lanes to decode, from 1 to 4 lanes. There is also a tearing effect signal detection function. When the DE pin toggles, the event is recorded and shown in a new column in the report area. This feature requires an additional LA probe. You can also capture waveforms to check for any connection issues. Open the waveform viewer and capture again. To speed up the process, we've set the memory usage to 5%. Please note that this waveform mode is intended for connection debugging only, not for protocol analysis. If signal integrity is poor, for example, if lane 3 is disconnected, the waveform display will clearly show the issue. You can also check the clock frequency by right-dragging across the waveform. Here, it shows around 450 MHz. Next, the trigger feature lets you trigger external equipment using ECC or CRC errors. For example, to sync with an oscilloscope for analog waveform capture. There is also external trigger in. You can use an oscilloscope to send a signal and let the bus finder to start capturing. You can also trigger on specific DSI packets by selecting high speed or low power mode, transfer direction, data type, and specifying a 4-byte header and 28-byte data to precisely target the data. Next, the filter feature lets bus finder capture only the first few bytes of each packet, significantly reducing memory usage. For example, since a command packet typically contains fewer than 200 bytes, you can set a limit accordingly. This allows the bus finder to capture data over a longer period of time. The timing setup function fine-tunes the signal edges to adjust the phase of the signal captured by the FPGA. Just click Run to let the software auto-calculate, then click Apply to finish. If you follow the wiring instructions correctly, you should be able to skip this step. The bus finder uses oversampling technology to capture data, so it remains stable across various signal speeds or even during dynamic speed changes. So far, we've successfully captured DSI signals at 1.94 GHz, and CSI signals at 2 GHz. Bus finder supports multiple options and helps you measure all kinds of high-speed signals. For more information, visit our website.